So in the previous video, we learned how to use Gaussian elimination to take a matrix, typically the augmented matrix for a system of equations, and write it in row echelon form. Row echelon form being the augmented matrix equivalent of what the system of equations look like after you have finished the process of eliminating as many variables as possible in the system. So now what I want to talk about is, okay, if you have the augmented matrix for a system and you have completed Gaussian elimination on that augmented matrix, how do you read the augmented matrix and figure out what the solutions to the system must be based on what the augmented matrix is telling you? So overall, if you have a system of equations and you're solving that system using this linear algebra approach of Gaussian elimination, the overall process is as follows. You start by taking the system of equations and writing the augmented matrix that represents it. You go ahead and perform row reduction on that matrix. You perform Gaussian elimination on that matrix and write it in row echelon form. Once the matrix is in row echelon form, you take that augmented matrix and you write it back again in terms of the original variables in the system. And I'll show you how to do that. And then you finish solving the system using back substitution. So let me demonstrate this four-step overall process in the context of the following system of equations. So the very first thing that I would do if I was solving this system of equations using this new linear algebra augmented matrix approach is I would write down the augmented matrix for this system. So on the left-hand side, I'm going to have the coefficients for the system. So the coefficient of x is 3, the coefficient of y, the coefficient of z, and then 0. And you can put a little vertical bar in here just to help remind you that these values in the right column are coming from these outputs in the system. Write down the coefficients of x and y and z from the second equation, as well as the output 11 on the far side of the equal sign. Write down the coefficients 1, -2, and 3, and then 7 over here on the far right side. So this would be the augmented matrix for the system. So notice that this matrix is for sure not in row echelon form at this time, right? Because the pivots are totally in the wrong position at this moment. You have an entire stack of pivots in this first column. So they definitely don't have this staggered nature where the pivots move to the right as we go down the rows. So we need to clear out these pivots in the first column. And as I mentioned in the previous video, when I'm doing row echelon form by hand, my preference is to, whenever possible, put a 1 in this top position because that will make it easier to do the scaling and the addition to cancel out the pivots underneath that 1. So just commenting my steps here, I'll say I'm going to swap row 1 and row 3. So that's going to turn my first row into 1, -2, 3, 7. And it's going to turn my third row into 3, 4, and -2. Once again, if you have access to a graphing calculator that can do this for you, go ahead and use a graphing calculator for it. But for folks who may not be able to afford a graphing calculator, I'm just going to go through this process by hand. So now to eliminate this 2 underneath the 1 in the first column, create a pair of opposite terms by scaling row 1 by -2 so that I get a -2 here to cancel out this +2. And then I'm going to add that into the second row. So let's see, that's 1 times -2 plus 2. That gives me 0 in that position as desired. Then -2 times -2, that's +4. +4 plus -3 gives me +1. Then the third column, 3 minus 2, that's -6. -6 plus 4 gives me -2. Then 7 times minus 2 is negative 14. Negative 14 plus 11 is negative 3. Alrighty, having created this 0 in this position, now let's create the next 0 that we need as we move down the first column. So to cancel out that positive 3, I'm going to turn the 1 into a negative 3. Add that down. So we have negative 2 times minus 3, that's 6. 6 plus 4 is 10. We have 3 times minus 3, that's minus 9. Minus 9 plus negative 2, that's negative 11. And then finally in the constants column, we have 7 minus 3, that's negative 21. Negative 21 plus 0, so that's negative 21 back here. Okay, so next, let's move to the next pivot in the matrix. The next pivot in the matrix is currently located right here, dead center. So I need to cancel out the pivots underneath that position. So I need to get rid of that 10. And to get rid of that 10, I'm going to scale row 2 by, in this case, negative 10. Again, I have a really simple scaling factor here because there's a 1 in this pivot position. Then we have minus 2 times negative 10, result 20. 20 plus negative 11, result 9. And then we have negative 3 times negative 10, result 30. 30 plus negative 20, result 9. Okay, so now we have performed Gaussian elimination and we have arrived upon a matrix that is currently in row echelon form. So we can stop the Gaussian elimination process here. So now that we have stopped the Gaussian elimination process, we can return to thinking about this in terms of the original variables and the system of equations. Let's remember that this first column is storing the coefficients of x. This second column is storing the coefficients of y. This third column is storing the coefficients of z. And this final column is corresponding to the outputs. So if we bear that in mind, we can take this augmented matrix and turn it back into a system of equations involving variables. So for example, that first equation has the form 1 times x minus 2 times y plus 3 times z equals 7, from the coefficients in this top row being applied to these variables, the vertical bar becoming this equal sign, and the output 7 appearing here on the right. Then doing the same action on the second row, we have y, we have negative 2z, and we have equals minus 3 on the right, coming from the second row, turning it back into an equation. And finally, this third row would be 9 times z, and then equals 9 on the right side. So notice that the equation coming out of the bottom of this matrix has every variable eliminated from it except for the final variable z. So at this point, actually solving for the value of z is trivial. Z is just equal to 1 in this case. Once I've found the value of z, I can start back substituting. For example, if I put that z value into the equation directly above it, I can find y without much trouble at all. Based on these results, the value of y would be negative 1. And then based on those results, if I substitute both of those values into this first equation, I can find the value of x immediately. So based on that, I would be getting a value of x is equal to 2, I guess. So based on that, my solution to the system would be x, y, z is equal to 2, negative 1, and positive 1. So this is the overall process. Take your system of equations, rewrite it as an augmented matrix. Row reduce that augmented matrix. Once it's row reduced, the elimination part of the solving process is basically complete. So put back your variables and then interpret those for the values of x and y and z that you are solving for. Rather than spend too much more time on the process of Gaussian elimination, let me just go ahead and give you an augmented matrix that someone else has already row reduced, a matrix that is already in row echelon form. And let's just get some practice interpreting this augmented matrix and understanding what it is telling us about the solution set to the corresponding system of equations. So for example, suppose somebody has an augmented matrix for a system, they did the row reduction, and after row reduction, they arrived upon this matrix right here in row echelon form. So if this is the row reduced augmented matrix, what are we understanding about the solution set? We have the first columns, which are representing the coefficients of x, y, and z. And then this last column we understand to be the outputs of the system, this extra column that has been attached to create the augmented matrix. This final column here is the outputs column. So based on that, let's go ahead and write down the three equations that correspond to this particular reduced augmented matrix. We have x plus y plus 2z, and then equals 0. We have 3y plus 4z is equal to 1, and we have 5z is equal to 10. So this is the system of equations corresponding to this reduced augmented matrix. So because this final equation already has x and y eliminated, we can solve that for z pretty easily. It's equal to minus 2 in this case. And then we just have to back substitute into the next equation to find the variable y. 3y minus 4 times negative 2 is equal to 1. So that implies that 3y is equal to 9, if I've got that right. So y is equal to 3. And then back substitute both of those values into this first equation. So we have x plus y equals 3 plus 2 times z equals negative 2, and that's supposed to equal 0. So that forces x to be equal to positive 1, I think. So we get the solutions x, y, z equals 1, 3, minus 2. That would be the unique solution to the system of equation that corresponds to this reduced augmented matrix. Supposing someone was going to solve a system of equations using this linear algebra technique. They created the augmented matrix, they performed Gaussian elimination on that augmented matrix, and the result that they obtained is given to us right here. If this is the reduced augmented matrix they obtained, let's figure out what that is telling us about the solution set to the corresponding system. So once again, we understand the first three columns to be telling us about the first three variables, x and y and z. And the final column of the augmented matrix is telling us about the outputs of the equations in the system. So let's go ahead and write down the equations that would correspond to this reduced augmented matrix. So we have x, 1x plus 1y plus 2z equals 0. We have 3y plus 4z is equal to 1. But look at what is going on in the last row here. In the last row, we're seeing that the augmented matrix contains completely all zeros in the first three entries here. So that's 0 times x plus 0 times y plus 0 times z. So 0, just 0, on the left-hand side of that bar there. But on the right-hand side of that bar, that 0 is supposed to equal 2. And that's a big problem because 0 cannot equal 2 no matter what. So the issue is that, after row reduction, we ended up with a pivot. We ended up with a non-zero entry here in the outputs column. And when we ended up with a pivot in the last column of the augmented matrix, this is a huge red flag in terms of the system actually having a solution. Because in a situation like this, if you have a pivot, if your first non-zero entry in the row occurs to the right of the bar of the augmented matrix, then that corresponds to an impossible equation like 0 equals 2. And this is the indicator that the system has no solution, or we put it another way, we said that the system is inconsistent. So that would be the conclusion that we would draw about the system based on this augmented matrix given to us in this example. It had a pivot in the outputs column, huge red flag, because that corresponds to an equation like 0 equals some non-zero value, which means that the system cannot be satisfied. Another example, here is our reduced augmented matrix. If our reduced augmented matrix has this kind of format, what is it saying to us? So in this case, once again, let's go ahead and rebuild the system of equations that would correspond to a reduced augmented matrix like this one. So here we have x plus y plus 2z equals 0. We have 3y plus 4z equals 1. But then in this case, the bottom row of the reduced matrix has all and only zeros inside of it. So if I were to translate the bottom row back into an equation, it would have this trivial form 0 equals 0. So we're in that situation where we have three variables, but at the end of the day, we only have two meaningful equations. And since we have three variables, but only two meaningful equations, what that means is we have one free variable. One variable whose value could be freely chosen to generate any of the infinite number of solutions to this equation. So this particular system is underdefined and it has infinitely many solutions. So let's do one more example of another situation where our augmented matrix has a bunch of zeros inside of it. So suppose that our augmented matrix in this case has 3 columns and 4 rows, and those bottom 2 rows consist entirely of zeros. Now, don't jump to conclusions too quickly here. Go ahead and take the time to write down the system of equations that would correspond to an augmented matrix like this one. We have 3 columns in this augmented matrix. So the first one would correspond to our first variable x, the second one would correspond to our second variable y, and the third column would correspond to the outputs. So if I translate these rows into equations, I get 1x plus 1y equals 2. I get 2y is equal to 4. And then the last two equations in the system come from these last two rows. 0 equals 0. All zeros on the left, all zeros on the right. Now notice that even though we obtained two equations that are trivially true, in this case, we don't have any actual free variables. In this case, we have two variables and we have two meaningful restrictions on those variables, which are giving rise to a unique solution to this system. The second equation is going to pin down one specific value of y, and then when we back substitute it into the first equation, we still end up with one specific value of x. So this system, despite the rows of zeros, still has a unique solution. In this case, the solution where x and y are equal to 0 and 2 respectively. So a row of zeros doesn't automatically correspond to an underdefined system. It really is about how many variables do you have and how many meaningful equations do you have that are placing restrictions on those variables. If you have more variables than you have meaningful equations, then you have some free variables that you can manipulate at will. But if you have the same number of variables as you have meaningful equations, then that will pin down one specific unique solution to the system. So that concludes today's lesson. Today we talked about sort of the full process of solving a system of equations using linear algebra techniques. Step number one is to take that system of equations and write down the augmented matrix that represents that system. Then row reduce that matrix, either by hand or using computer assistance, depending on what you have access to in the moment. Once you have row reduced your augmented matrix, go ahead and translate that back into a system of equations in terms of your variables x, y, and maybe z. And then interpret those equations that you have written down and figure out what the solutions might be to that cleaned up reduced system. In certain cases, as before, your system will have a single unique solution. And this occurs when you have no impossible requirements in your equations, and you have as many variables as you have meaningful real restrictions upon those variables. So if you have three variables and you have three meaningful restrictions, and none of the restrictions are impossible, then that's going to give rise to a single unique solution. By contrast, if you end up with a pivot in the outputs column of your augmented matrix, where you have zeros to the left of the bar and you have a non-zero value to the right of the bar, this is a situation where when you translate that row into an equation, it's going to be an impossible requirement to fulfill. It's going to be something like 0 equals 2 or 0 equals 5, and you cannot make 0 be equal to a non-zero value. So this is a situation where the augmented matrix is telling you that your system is inconsistent and there are no solutions. By contrast, if you have a row in your matrix that consists completely of zeros, there is a chance that your system is underdefined. Really, what you need to do is take stock of how many variables your system has and how many meaningful equations your system has as well. If you have more variables than you have meaningful restrictions, then you have a free variable which will give you infinite solutions. But sometimes, despite rows of zeros, there is a matching between the number of variables you have and the number of meaningful restrictions that you have. And so it's still possible to get a unique solution even if your augmented matrix has all zeros in a couple of its rows.